So let's keep going on part 1.2 of our chemistry unit. So it says emissions can react. So emissions from combustion reactions react with water to form acid rain. Most of these emissions are anthropogenic, which means they come from human activity. Rain is naturally acidic because of its carbon dioxide that is naturally in the atmosphere. So acid rain occurs when precipitation has lower than normal pH. Okay, so there's naturally already going to be some carbon dioxide in our rain. So that adding of certain, things that we're burning and gases and stuff that go into the atmosphere, those are going to mix with the water in the air, the water vapor that becomes rain, and make the water that rains down onto the earth a lot more acidic than it should be. So the following table shows various oxides we have discussed, which react with water to form acids. So these are the ones that we talked about in the very first section. So it talks about carbon dioxide added to water gives us carbonic acid. That's this. So that's carbonic acid. Then sulfur dioxide in water gives us sulfurous acid. Sulfur trioxides added to water give us sulfuric acid. Nitrogen, NO, with oxygen in the air gives us NO2. And then the NO2 with water gives us two different types of acids, so nitrous and nitric, depending on the type of nitrogen oxides that are in the air. Okay, so we've got carbonic acid, sulfuric acid, sulfurous acid, nitrous acid, and nitric acid, all falling from the sky, if we put that in perspective. So that's something that isn't necessarily, good. And that's why we need to, reduce the emissions that we're putting into the air so that there's not acidic rain falling. And maybe people are like, whatever, acidic rain, yeah, it's not going to bother us as humans. Really, yeah, in the grand scheme of things, it actually is going to bother us, but directly, no, we can go outside and it's not going to hurt us. But that is affecting like the waterways, so plants and animals that live in rivers, in the ocean, stuff like that. That's all going to change the pH of the water and affect things that can live in that area. And certain things need to live there for us to eat and stuff like that. So it is important for the ecosystem that we reduce our acid rain. All right. So I just said it's going to reduce the pH. So what the heck is pH? Well, pH is a value that represents the concentration of dissolved hydronium ions, H3Os, in a solution. Concentrated acidic solutions have greater amounts of H3O per mole of solution than diluted acidic solutions. Okay, so the more H3Os you have, the higher your pH. And by higher, I mean lower your pH, because low pH means you're acidic. But we'll get to that in a second. The concentration of H3Os influences the reactions involving acids in the following way. So the more H3Os you have, the more quickly the solution will begin to react. How much change the acid can cause. So the more H3Os, the more acidic something is, the stronger acid it is. It also affects the amount of base required to neutralize. So the more H3Os, the more base you're going to need to neutralize that acid. And the amount of base of metal it will react with. So the more H3Os, the more reactive that's going to be in general. A pH scale was developed in 1090 as a means to communicate the acidity of solutions. So the acidicness or the pH scale was created a long time ago, and this is sort of how it goes. So I always, and you guys, this is not new, neutral is around 7, all right? And everything that is less than 7 is going to be an acid, and everything greater than 7 is going to be something that we consider a base, okay? So if we look on this scale, this sort of tells us some things that we might need to know. So battery acid is going to be our most acidic thing on there. Lemon juice, vinegar's around the 2 to 3 range. If your water is around that range, that says when adult fish die. Fish reproduction is affected at the 4 to 5 range. Within all of that range, we've got from like 1 to 5. That's all in the acid rain range. So acid rain can rain down to being that acidic. And that can affect, obviously, fish. A normal range of precipitation is between 5 and 7, I guess you could say. So that's pretty normal for our precipitation or our rain. Milk is around the 6 to 7 range. A normal range of stream water, so the water that we see in a stream, should be between 6 and 8. Baking soda, seawater is around the 8 range. Milk of magnesia, that's a type of medication, sort of what you would find in like Tums and stuff. That's going to be around the 10 to 11 range. Ammonia near the 12 to 13. Lye, probably around the 14 range. Okay, so as you become more and more basic, you have a higher and higher number, okay? And 7 tends to be the highest pH, the neutral pH. So pH is a logarithmic scale. This means that a change in pH of 1 is equal to a 10 times change in hydrogen concentration. All right, so if we have how much concentration of hydrogen H3Os at a 0 pH, well, it's 1 times 10 to the 0. And then as we work our way up, we become less and less. So basically it's 10 times less in each level as we go up the pH scale, okay? So at 0 pH, it's 1 times 10 to the 0. At 1 times 10 to the negative 1, and so on and so on. So it makes it a whole lot less hydrogen ions as you go up, like considerably. How do we calculate pH from a hydrogen ion concentration? Well, our pH is equal to the negative log 10 of the concentration, okay? And I don't even have a scientific calculator. To be able to do this. But I will try as I'm doing this. You guys have them in the class. I just, okay, I'll try this. I just Googled it. So it says a sample of lake water has a hydronium ion concentration of 2.27 times 10 to the negative 7. Determine the pH. So literally we're just taking this formula going pH is equal to negative log. Your calculator should be a log base 10. When you write it into your calculator, make sure that it puts a little 10 there. You don't have to put the 10 there, but it should be there. If not, then make sure you put it. And then the concentration, which is 2.27 times 10 to the negative 7. Okay? So when you're putting this in your calculator, I'm not sure if I'm going to be able to do this on this. I'm just going to try. That's definitely not a good calculator. Let's see you can put this into your calculator better than me. I can't even find the log button on this calculator. I wish I had a calculator home, but I didn't know that I was gonna be home and have COVID. Not something you plan for, obviously. But you guys can put this in your calculator to get the right answer, hopefully. I can't figure out this calculator. I wish that I had a proper calculator, but that's how you would formulate it, and you should get, your answer should come out to an answer that is obviously between 0 to 14, right? So this answer, if it's not between 0 and 14, then you've done something wrong, okay? Now, the way that we would calculate our H3O concentration from our pH is basically the opposite of that. And the opposite of that is by taking 10 to the negative pH, okay? So if we're using this formula, it says calculate the concentration in a shampoo with a pH of 5.72. So all we got to do in our calculator is go the 10 to the button, and we're going to say negative 5.72. Okay. And when you do that, you should get your answer, and that would be your H3O concentration. Okay. So there's some practice problems there that you can try out in your book. Okay. I'm just going to keep going. And the last section here is on indicators. So substances that change color due to a pH of a solution. And you can find this table in your data booklet. Let me see what page it is. So this is your data booklet you guys should have. Flame color, no, right here. Yeah, okay, so that is on page 12 of your data booklet, and I should write that there, if I can. Oh my gosh. So that's on page 12 of your data booklet. But this is showing you sort of like, if we use a certain indicator, and we can put it in, mix it in our substance to see what color it changes. So if we had a substance that was between 0 and 1.6, we could put the methyl violet in it, and it would change depending on what the pH is. So if it was 1.6 or higher, then the solution would turn blue, okay? If it's, I don't know, between 0 and 1.6, let's say it's like 0.4, it should be closer to yellow than blue. Maybe you're gonna, if you find something in the middle, might be green, okay? So knowing that those pHs aren't gonna give you an exact pH, but it's gonna give you a relative range or sort of an area to zero in on when you're using that. So using indicators to determine pH, it says use the acid-base chart to determine the pH range. Use a number line to narrow down the range of values. Okay, so we're going to do an example question here on how you would use this information to sort of figure out when we're doing this in a lab. And hopefully next week, if we have time, we can do a lab on this. So it says a solution is tested with 3 indicators. Here are the results. So we got some unknown solution, but we've got some results from it. So the first thing I'm going to do is I'm going to draw a line. Mostly because I want to be able to zero in on where the heck this solution is. So our first indicator is bromothymol blue. So we are going to look go back to this page and we're going to look for bromothymol blue. So where's bromothymol blue? It is right here, okay? Bromothymol blue, it detects between the 6 and 7.6 range, okay? So that's where I'm going to, so we're at 1, 2, 3, 4, 5, oops. I did not do a very good job at this. I'm going to start my line over again. All right, so our bromothymol blue, go back to it, is between 6 and 7.6. So I'm going to, because it's called bromothymol blue, I'm going to use blue. So 6 to 7.6. So it's like right in this range. Okay, and maybe I'm going to write that in there. 6 to 7.6. Okay, that's bromothymol blue. Let's look at the next one. Phenolphthalein. So phenolphthalein is right here. Oops. And it is between 8.2 and 10. Okay? And that goes from colorless to pink. I'm going to use pink just because that's, now I'm already forgetting how it goes. 8.2 to 10. So 8.2 all the way to 10. So it's in this range. Oops. And our last one is phenol red. And phenol red, oh, it's in between. I couldn't find that one. And that's between 6 and 8. So between 6 and 8, right there. So I guess that's a really small range, and maybe I should, like that, like the actual example, it only shows this range. So we're only going from 6 to 10. So I guess I could zero in on that area. 6, 7, 8, 9, 10. All right. So now we got to figure out what the color comes up with. All right. We know the ranges of these, and maybe I should write it right beside it. Maybe my lines. So this one goes from 6 to 7.6. This one goes from 8.2 to 10. And this one goes from 6 to 8, all right? And by doing this, we can actually figure out generally what the range is. All right, so let's look for bromothymol blue. When we used bromothymol blue, it turned blue, okay? So let's look at bromothymol blue. It's right here. It goes from yellow to blue, all right? So blue is the high range, which means that this is, if it's blue, we had to assume that it's at least 7.6. All right, so for bromothymol blue, what we're gonna, if it turns blue, which is what it said, we're gonna have to assume that this is gonna be 7.6 or greater. okay? Let's go to the next one. Phenylphthalein is colorless. So let's look at this. So colorless means that it's 8.2 or less. All right, so I'm going to write that here. And then the last one, phenyl red, turns red. And red is the higher scale of it. So then we're going to say that that's 8 or higher. So this is, let's put this on our line. So for bromothymol blue, it says it's 7.6 or greater. So where's 7.6? So we're going to have to guess that it's 7.6 or greater. That's in that scale, okay? Phenylene says it's 8.2 or less. All right, so that second one, 8.2. Where do we got 8.2? Let's say it's right there. 8.2 or less. I'm only going to go to as far as we know that one to be. And then the last one is phenyl red. That could be 8 or higher. So 8 or higher. So really, the only range that this can be in is where all of these colors are together. So that's right here to here. And it's not even that far. It only goes to, what does the yellow one go? So 7.6 or greater, 8.2 or less, and 8 or higher. Okay, so what that tells us is that it has to be between 8 and 8.2, if that makes sense. Because it's higher than 7.6, it's less than 8.2, and it's more than 8. Okay? So that tells us that it's between 8 and 8.2. And that's what their picture is a whole lot better than mine. But that's the process that you need to go through to figure that out. So they did their scale, and they showed where phenyl red, bromothymol blue, and then phenylene was. And they figured out that, yeah, it's between 8 and 8.2. So although we don't have a fancy machine or something that tells us exactly what a pH of something is, we could use indicators to narrow it down. Between 8 and 8.2 is like pretty like close, solid evidence to explain that. Okay? So let's try this one. It says, what would the pH of a solution be that is colorless in phenylphthalein? So colorless. I'm just writing it down here. Yellow in phenyl red. Orange with chlorophenyl red. and blue and indigo carmine. All right, so let's figure out this. So let's start with phenylene or phenolphthalein, and it's colorless. So what is that going to be? So phenolphthalein here, colorless, is on the bottom range, so it's 8.2 or less. So I'm just going to write less than 8.2. Okay, it's yellow and phenyl red, so let's figure out where that is. Phenyl red, yellow is our low range, so it's less than 6.6. Orange in chlorophenyl red. Chlorophenyl red is right here, and it's orange. If we look at this, it goes yellow to red. So if it's orange in that, we know that it's in between 5.2 and 6.8. So we know it's somewhere in between there. We know that if it's orange. So I'm just going to write that full range there. And then blue and indigo carmine. So that's right here. Blue means that it's on the low range, so less than 11.4. Okay, so this doesn't, literally this tells us basically nothing. I shouldn't put a line through it, but less than 11.4, well, that's not really going to help us much. We already know it's like less than 6.6, right? So this information here is key because we're saying it's less than 6.6, it's less than 6.8. We already know that it's that because it's here. So to be honest, this information doesn't really matter. This information is an outlier, it doesn't matter too much. We're going to look at the middle part here. So we know that it's less than 6.6. So if this was between 5.2 and 6.8, because that's what the chlorophenyl red is, if it's orange, we have to assume that it's probably somewhere in the middle. So if we want to figure out the middle of this, what we can do is we can go 6.8 minus 5.2, and that's 1.6. So there's a 1.6 range in between there. So we need to find where halfway in between 1.6 is. And that is at 6, I believe. Yeah, because 5.2 to 6 is 0.8, and 6 to 6.8 is 0.8. So the middle is 6. So if we're thinking that an orange would be around the 6 mark, then that makes sense. And that the phenyl red is only telling us that it's less than 6.6, which we know because it's in the middle range. So we really we don't know for sure, but we can probably narrow it down to the fact that it is at least between 6 and 6.6, I'm gonna say, because we know that it's less than 6.6, and we know that it's around the orange mark, so it's in that range. That's what I would put as that. If you wanted, we don't know for sure that it's 6 right on the dot, but we know that it's in that orange range, so it is in between the red and yellow. Okay, and maybe if you were to look at how dark that orange is, you might be able to maybe narrow it in a bit more, but really we're just gonna know it's in that range. Okay. So now there's some practice problems to go along with that. All right. So that is the end of that section. So try that out, and we will start on topic 1.3 probably tomorrow.